Today I'm going to present you my article that is called Robust Outdoor Positioning via Ray Tracing, which I was prepared during my studies in MIPT. So firstly, I would like to give a short overview of some positioning techniques that can be used in 5G. First of all, it's positioning based on ID. It's used in 5G also. Then it's different power methods when we can measure the distance between user and base station based on the power. And if we have distributed architecture, its metric can help us to increase accuracy much more. So next method is based on round trip time. It is presented in standard, in 3GPP also, as well as uplink time difference of arrival and downlink time difference of arrival methods. And also there are a group of methods that based on angle of arrival estimation or angle of departure estimation based on the type of measurements and signals that we use in downlink or uplink. In uplink, we typically can use sounding reference signal for angle-based estimation and positioning reference signal based for downlink methods. So on the right side of picture, you can see CDF for error of different positioning methods for angle-based ones. So why do we decide to choose angle-based methods for positioning? First of all, it's because of for the last previous years, we have much larger antenna arrays of base stations. So it means that we can exploit this property to increase accuracy of positioning methods, because to position to find the location of the user by time, we have to provide very accurate clocks on every receiver, which is very expensive. So let's look at the picture. We see that here that green one is the best. Its picture is taken from this article. So the green one is uplink angle of arrival method. We use this one for future disclosure. So let's also take into account the network, and we consider distributed 5G network when we have some central unit and some number of distributed units, which are connected with some control interfaces, and they can exchange measurements between each other. We do not take into account any access and mobility management functions, location functions. We assume that they exist, and we want to present some technique via ray tracing that will provide us much better accuracy than GPS or than something that is already studied in 3GPP studies. So let's look at their system model. We can see the typical outdoor urban environment model. We modeled channels via developed C++ ray tracing simulator, and antenna configuration is typical. It's horizontal array, 3x8 antenna elements, and 2GP radiation pattern. Typical carrier frequencies are presented here, and the most of hard processing is done by CPU, somewhere in the cloud. On the right side, you can see example of studied environment. So this slide is a brief explanation of proposed positioning architecture. We have some remote units which can receive signal in uplink. We used sounding reference signal, and each unit estimates angle of arrival spectrum. For example, by music algorithm. It doesn't matter which one to use. We just present the overall architecture and study the accuracy of this approach. Next one is estimating angular arrival spectrum, and after that, when distributed unit estimated it, it finds angles of arrival and passes them to some cloud unit. Cloud unit contains very complex map, 3D map, which can allow him to trace rays. So after he received instant angle of arrival estimate, he launches ray tracing search in the directions of arrival and localizes instant positions of user equipment with probabilistic weighting. So after this step, we can estimate exact position of user equipment, which was at the previous step when we received angle of arrival estimates. So next steps are optional and can be used as some features to improve accuracy of our algorithm. And as we can show later, it really helps us to estimate positions better. So one of the features is to detect localization pattern of user equipment and discard the candidates of positions that we got after probability weighted positioning. Next one is clustering of candidates and selecting the most appropriate cluster. And the last one is tracking. So let's move to ray tracing model, which we used during our simulations. And then we will discuss in more details the positioning algorithm. We modeled channels via ray tracing simulator, which was based on outdoor environment, which got from OpenStreetMaps, and we also got the locations of radio remote units from open map from operators. We have such one in Russia. So we know where is operator really located and place them at OpenStreetMap, which was also given to us. And this model is very realistic and can help us to work in real conditions in Moscow environment. So after we got this ray trace, this outdoor environment, we can do channel modeling. It's based basically on 4 patterns of ray propagation: is free space propagation, then reflection, scattering, and diffraction. It's well-known techniques. I don't think that it's important to disclose it here. Maybe it's very important to mention that some scattering models were previously studied, and single lobe directive model, which is presented with this formula, is chosen for future simulations. And also diffraction is based on formula that presented in 3GPP to model diffraction. To achieve very good accuracy, we also have to track a lot of rays. So it will be thousands and thousands of rays, and we have to do it very fast. Of course, we have done it in C++ and used some acceleration techniques like wrappers, parallelepiped or spherical based on objects. We have, for example, for outdoor objects, we use parallelepiped wrappers, and for user equipment, we use spherical ones because it's faster. After that, we performed hierarchical storage of outdoor objects to perform simulations much faster. Also, we tried to launch arrays hierarchically so that we will be able to track as little arrays at each moment as possible, so that we have to predict, we have to follow some minimum accuracy of space accuracy, and from this condition, we have chosen number of rays which we have to trace, and at each moment we update each ray with several ones. Also, we can use parallel intersection tests to increase accuracy, and not to increase accuracy, to increase time, to decrease time of modeling. Positioning algorithm starts from angular spectrum estimation. It's based on music algorithm, and it has the following formula for angular spectrum estimation, and the steering vector of antenna panel is presented here. After we estimated spectrum, we use cell averaging constant phase alarm ray detector and find two arrays, two angles per each array. So what the problems can be here? The first problem is miss of direction. The second problem is extra direction. And one more problem is noise estimate due to interference, due to AVGN noise, due to inter-RRU calibration errors. And these problems are solved via several approaches. For example, noise angle of arrival estimate is solved by weighting of each received array inside each search area, which we select based on accuracy of calibration of our unit. False extra directions can be solved by clustering of candidates of locations here, and miss of arrival direction, we do not know how to solve it, but we can say that it's partially solved by cooperative multi-point reception, so that we have a lot of other remote units, and it's not a big problem that some directions will be missed. And also, which is much more important, that we have a multipath propagation in typical outdoor environments, which help us to get, for example, 5 rays per antenna panel, and it's not a big problem, it's not a big deal when the only ray is missed, one of 5. Of course, if we had a lost channel, it will be harder to use this technique, but in urban environment, this helps us to cope with misses. After we estimated angle of arrival each unit, we send this estimate to central unit, which estimate joint spatial probability density. It's made by weighting each position by some weight omega, which is can be found by Bayesian approach, which is commonly known. It goes if we have a max minimum problem, we will find that Bayesian approach will be the best in this case, and the weight can be found in this manner. Omega estimate, it's the estimate which we got from distributed unit, doesn't matter, it's azimuth or elevation. Omega bias, it's angle deviation that we search. For example, we received 45 degrees and we search in plus minus 3 degrees. Omega bias in this case will be plus minus 3 degrees. And we can use weighting P by normal distribution. It's not optimal. We cannot find the optimal solution here because we do not know the real distribution of time errors. But seems to be that it's a mix of uniform and normal distribution, maybe Cauchy distribution, something like this. And in this case, maybe something about normal distribution rates will be optimal here. The main problem here is that we have a lot of candidates for estimating weighted position. We can solve this problem by selecting only some of them, and after we rejected lower probability ones, we will have which are much better and much more probabilistic, and we will not lose the original candidate because the most of false candidates come from additional errors from inaccurate maps. So on this slide, you can see positioning error for both cases, for loss and in loss case, after weighting with proposed approach. In loss case, accuracy for ±1 degree synchronization of an antenna panel is about 1.3 meters per 90% probability. For NLOS case, it's much worse, and that's why we want to perform next step. For loss case, this algorithm works very good, but we need to add some more features to our ray tracing model to cope with NLOS cases, as they produce a lot of errors. We proposed optimal position selection, which is based on different metrics from ray tracing model, for number of rays, number of reflections of rays, number of reflections per each array, which we got from buildings, maybe closeness of reflected or scattered array to the edge of the building, simple loss and NLOS recognition. This will be studied and uncovered a bit later. A number of base stations which see the particular user equipment, powers, and specific hardware limits of antennas. It's very important to mention that although this step contains a lot of parameters, which has very low complexity compared to ray tracing model, and it helps us to achieve much more performance gain for NLOS cases with a very low complexity if we store some ray tracing outputs. Here we have some open questions like what is how to get the maximum description with the minimum number of outputs from ray tracing model. It's open question because we don't exactly know how to describe the error. If we find their model characteristics that describes the error very correctly, this means that we can find firstly the error of our estimate, and then it means that we can fix our error when we know some correlations between internal error and pattern which we got. And the next question is how to train pattern recognition with real measurements. In this model, we trained it with simulated measurements. We have shown that we have very good correlation between estimated error inside our model and real error. And we trained it with this assumption. But it can be better enhanced when we use real-time measurements in uplink. After we done optimal position selection, we should also perform some clustering algorithm to reject positions from interference directions from music algorithm. It's done by a very simple algorithm. When we first estimate table of distances, then perform depth first search and find clusters of each, find centers of clusters and perform its tracking in next steps. So here is a representation of our simulation results. This table shows that depending on number of base stations, we can predict accuracy of our estimations. For one dedicated base station, which can receive each signal from UE, we have about 15 meters per 90 percentile, and for 5 base stations, which can cooperate to each other, we have about 1 meter, which are very good and optimistic estimate. This picture shows us how does our clustering algorithm works, and we see that blue corresponds to clustered positions. We see that how many positions have we tried to reject by our algorithm, and in fact, despite this have very low probability, it's a lot of them, and they will influence an accuracy about blue ones. On the right side, you can see positioning probability, CDF of positioning error after clustering is done. We see that it's for loss and in loss case in one plot. Of course, the most cases are NLOS. And we see that the best strategy when you combine the maximum probability, posterior probability, clusterization, and most expected position maximization average in cluster. And we see that if we combine both of this strategy, we can provide the error, which is very close to loss case from the previous slide. And it means that we were able to cope with NLOS outliers from very low accuracy of a digital map and from inaccuracy on angle of arrival estimation. Also, this slide presents how does inaccurate maps influence the positioning accuracy. We done these simulations and compared them to estimates done by Monte Carlo simulation in 2D space, when we know the probability of error of outdoor buildings, of trees, and so on. We see that if we consider that our map is almost correct, and the most errors goes from angle of arrival estimation, from noise in channel, we see that 90% percentile is about 1.3 meter. When we add error from transmission coefficient of buildings, we have a maximum of 1.7 meter error, and when we have unknown positions of buildings on maybe their sizes, we have 2.5 meters. It's, of course, it's 2 times higher than made from ideal map, but it's still in range. So it is still better than GPS measurements, as we will see later. And the question here also is how to improve accuracy of our maps. And the first solution that we found that, but did not study it, is application of GAN models for calibration these maps with real-time uplink measurements. And the second proposal is to use RTK receivers to calibrate our map offline. But the second approach is maybe worse, because outdoor model, despite outdoor is more stable than indoor, but we think that we will need to calibrate map with ATK receivers much more often than just once. So it will be a very expensive solution. Better, I think, is to use GAN models for online calculation. But here will be the problem of traffic. So we're not sure that it will be possible to do. Also, we provided a tracking algorithm in Angular and in space domain. Each line was fitted with mostly L1 optimization because, as I said previously, each angle of arrival measurement is a mixture of normal and uniform distributions, and L1 works in this case better than L2 optimization. Here, this picture presents general ideas that we used to create our tracking algorithm. We assumed that in Angular domain, each measurement changes linearly, which is very close to a real measurement that was done. And that was done in another article. We didn't measure this one. And also we assume that there can be red one is false interference angles. At some TTI they may happen a new angle, and we have to track them too. And in this model, we performed tracking according to this algorithm. We started at each TTI new trend, then check whether it's close to previous trend. If it's not close, we create new trend, track it some TTI, and if it is still a new trend, we will save it and continue. And also we have some model to track if the presented tracks are outdated, and we delete them if some TTI there is no new estimate. For the tracking in space domain, the model is very close to this one, and the picture below shows how this model can help us to find the true cluster of candidates. But there is a problem. We found that there is some bias between trend and real measurement that cannot be solved by proposed approach. But in Angular domain, there is no such bias. Here is the performance of tracking in Angular domain. We didn't present here space domain tracking, as it adds a little bit less performance gain than in Angular domain. We see here that in most cases, when the model adapts, it gets less than 1 error positioning accuracy, less than 1 meter error. And the most error happens when the user at this map changes its direction. In this case, the error might be up to 2 meters. On the right side, we see that green one, it's our predicted, green ones are estimates, and red ones are those which were predicted by our algorithm. And green ones are much closer to red or to blue, which are true angles of users. Next, we compared our simulations with real-time measurements, which were done in Moscow, also in the same map as simulated. and about 1,000 measurements were done via Samsung and iPhone. And we compared horizontal accuracy and measured accuracy. Horizontal accuracy is internal, which was estimated by software, and measured was estimated by Google Maps and real environments. We see that for GPS measurements, we see about 9 meters estimated by Samsung and about 8 or 11 meters estimated by iPhone. And via our algorithm in the same outdoor environment, we can achieve 1.2 and 1.5 meters in case of we have accurate map. And if we have inaccurate map, this number will be maybe 2 times higher, but 3 meters is still much less than 8 meters. So our algorithm will be better than GPS. Thanks for your attention. I am ready to answer all your questions if you have.